Okay, so I want to start off just by asking you a simple question. What is machine learning? This is actually going to be Q1 in the Google form that I sent out. So take a minute to think about it and type into the Google form what words come into your mind when you hear or when I say the phrase machine learning. Okay. So, a lot of common responses that I get previously are artificial intelligence, robots, some movies like Terminator or something like that. Um, and yeah, there's some reason to have those words come to mind when you think of machine learning. Uh, but for the most part, it's a lot of just linear algebra and statistics and a little bit of algorithms that come across from computer science too. So a little bit of history about machine learning. The term itself is not new by any means. It's been around for over 50 years already. There was a computer scientist who was creating a checker playing program, uh, and he kind of has this kind of ambiguous and abstract definition of machine learning as a field of study that gives computers the ability to learn without being explicitly programmed. This definition doesn't really mean too much to me. I don't think that there's anything wrong with it, but I don't think that it gives most of you a good picture of what machine learning means. Um, I would like to point out, though, that machine learning was never invented. It's not like one day uh, machine learning was created and prior to that, machine learning had not existed. The coining of the term in 1959 was really only one step in a series of dozens and dozens of steps that kind of like are culminating today in what we know as machine learning. So, one of the most common data fitting methods in machine learning is called the least squares method. We're going to talk about that quite a bit shortly after I give you a little bit of historical background and stuff like that. And that's been around for over 150 years. It was developed by a French mathematician in 1805. So, I mentioned this shortly ago. What we know as machine learning now is really just this culmination of a lot of different pieces from a lot of different fields of study and a lot of different developments over the past couple hundred years. But there are three kind of fundamental reasons as to why it's so popular right now. One of them is the abundance of data and data storage. So this is not in large part, this is because of AWS, which was developed in the I think late '90s, early 2000s, and really kind of set this new standard and this new ability to store large amounts of data and process large amounts of data. Along with data storage and cloud storage is computing power. So if you've taken 6UNA, I think that they talk a lot about how there's kind of been like this exponential growth in how computers have been able to process things faster and faster and faster. And then money. So companies have figured out how to make the above two, so cloud storage and computing power, they've figured out how to make those profitable for them. They've been able to leverage user data to make money. So that's what like is kind of keeping it around now, and that's why there's a lot of industry interest in it. So it is an evolving field. It's been around for hundreds of years and has been changing over that. Um, and it will continue to change. It's not like everything is set in stone and the way we do things today is the way we will be doing things 10 years from now. That's not necessarily going to be the case. Despite this, there are some kind of like underlying fundamental methods that we follow when we're performing machine learning. And when I say performing machine learning, notice how it's not just like a single act. It's more of like a sequence of events, and it's more than just one model. It's an entire life cycle of a data process. So here's this timeline here that I took from Google, from Google Images, and I kind of like it as a general overview of the steps of machine learning. Um, it's not perfect. Machine learning, as I'll talk a little bit about later today, but we'll really talk a lot about in the next couple lectures, is how machine learning is a cycle. It's not just a linear process. There's kind of a cycle to it, especially steps 3, 4, 5, and 6. So let me talk a little bit about each of these steps, though. So step 1, data collection. This is something that we haven't talked about at all this semester, and we likely won't. I know that there was some interest in learning a little bit about web scraping, which can be one form of data collection. We're probably not going to get to that this semester, but if you're interested in learning about web scraping, there are some great online tutorials for that. Another common form of data collection is sampling and surveys. So if you're interested in sampling, there's a great stat class. I think it's 152, which is all about sampling surveys. Data preparation is something that we're going to talk about 2 weeks from now, I think, when we talk about data cleaning and exploratory data analysis. Step 3, choosing a model. That's something that we're going to talk a little bit about today, but is really going to be the focus of much of the rest of this semester, when we kind of introduce you to a bunch of the most common and popular and useful machine learning models that are currently being used. Training is what most people think of when they think of machine learning. They think of, you have some model that is, you've picked arbitrarily, and then it's all about training. It's all about training your model. That's definitely not the case. Like this is obviously a crucial step, but there's much more to machine learning than just creating this cool model. Evaluation we're going to talk about today and a little bit in the coming weeks too, and how it's really important to evaluate your model safely and appropriately, and to make sure that you aren't messing things up. It's really important step. Parameter tuning, if you don't know what that means, that's okay. We'll talk about that a little bit later today and in the coming weeks. And then prediction. So notice how I said before that steps 3, 4, 5, and 6 are kind of like this cycle. Step 7, prediction, is ultimately the end goal of most machine learning models. And that's something that you ideally kind of like jump into once, where you make a prediction on maybe the held out data that you have on your test set, but then you leave it out and you predict once and then you never touch it again. So prediction is not ideally part of a cycle. You can predict on, I'm going to talk later about predicting on a validation set, on creating a separate mini data set to kind of like test your model. But once you start making your predictions, there are dangers if you basically try to make predictions too frequently. Then it can easily lead to something called overfitting, which we'll talk about in a couple weeks. Okay, cool. So, we talked about this linear flow chart here, which isn't really a great representation. It's more of like a cycle. But most of you are probably a little bit confused as to what machine learning actually is. So to help visualize it a little bit, I like this tree diagram here that was created by Joseph Gonzalez, who teaches Data 100 sometimes. I've seen this tree structure, this tree diagram come up many times in like over 4 different courses that I've taken here. It's really nice, and I think does a good job of kind of giving me and hopefully you a visual understanding of machine learning. It's not perfect. It's not all encompassing, but I think it really helps break apart the different pieces of machine learning. So let's start with this first split here, labeled data and unlabeled data. For today and for the rest of this semester, actually, we're going to be ignoring this middle part here, reward and reinforcement learning. This is something we're not going to be talking about at all this semester. We're going to, if you're interested, you can take a course like CS 188. They talk about reinforcement learning a bit. Otherwise, Data 102 also talks about reinforcement learning a bit, but we're not going to talk about it this semester. So first, I just want to introduce the difference between labeled data and unlabeled data. Labeled data is where we have our response data. We have our response vector y. It's known. Whether it's quantitative or categorical, we have our labeled data. We have our y. If you don't remember what a response variable is, I would recommend going back to the last lecture. I will be giving a more concrete example of a response variable in a couple minutes, though. Unlabeled data is where you have your features or you have your explanatory variables x, but you do not have your response variable y. There's no response. You just have the explanatory variables. So let's go into this unsupervised learning branch here first. There are two leaves down at the bottom, dimension reductionality and clustering. I don't really like that dimensionality reduction is here. This usually just refers to PCA, principal component analysis. If you've taken Math 54, you should know what that is. I think we might touch on it briefly later. It's not really what I consider to be a machine learning. It's not really a machine learning algorithm. There's no prediction going on. The only goal is to reduce the dimensionality of your data set. That's it. Clustering, on the other hand, is a little bit more in line with what we think of when we think of machine learning. Some of the more common clustering algorithms are k-means and a Gaussian mixture model, which is solved by the expectation maximization algorithm. We're not going to talk about either of those this semester. We might touch on k-means briefly, but we're probably not going to get to it. If you've taken Data 8, you might be thinking, wait, k-means sounds kind of like k-nearest neighbors, because k-nearest neighbors is the one algorithm that, well, not the one, but one of the machine learning algorithms that you talk about in Data 8. Do not get them mixed up, though. So k-nearest neighbors, KNN, and k-means are very, very different. Their names sound kind of the same, but they're pretty opposite. K-means is unsupervised. KNN is like a non-parametric supervised learning algorithm. Yeah. If you don't know what that means, that's okay. We'll touch on what those words mean later. So let's jump over to the supervised learning branch. This is what we're going to be talking about today and for most of the rest of the semester. You can see another split here where we have a quantitative response and a categorical response. So hopefully you know the difference between a quantitative and qualitative or categorical variable. In case you don't, quantitative, just think numbers. I always remember it because quantitative has an N, and N is the first letter in numbers. So think quantitative numbers, and then categorical, categories. Or qualitative is also another word for that. When we have a quantitative response problem, this is called a regression problem, where we try to regress some values on some other values. If we have a categorical or qualitative response, this is called a classification problem, right? So imagine that we have two different categories. So here they're in the little picture below, there are like pluses and O's or zeros. Those would be like two different categories that we have. Okay, so to kind of give you a cool demo of the power of just some very, very simple machine learning algorithms, there's this cool problem that I'm taking from a past CS 189 homework. I don't know if they would use the problem again. I'm not sure they might. But if they use the problem, then here's how it works. So I may have said this last week. I don't remember. But linear regression and the ordinary least squares solution to linear regression is by far my favorite machine learning algorithm. It's really interpretable. It's really easy to understand, and it's surprisingly effective. A lot of people automatically jump to neural networks and other, maybe random forests or boosting methods when they hear the words machine learning. But I always think of linear regression first. It's really fundamental, and most of the other learning algorithms also depend on it too. So back to this example here. Imagine that we have a picture of a tennis ball. As you notice, it's very bright, and the coloring is kind of hard to look at even. And then we have a picture of St. Peter's Basilica. So if you're a history buff, you might know a little bit about St. Peter's Basilica. I think it's in the Vatican. I don't remember who designed it. I think Michelangelo helped, maybe Bernini, some people like that. It's irrelevant for this example, but alas, here it is. And then imagine that we have a picture of a mirrored ball that was placed in St. Peter's Basilica in the exact same spot as this original picture was placed. Okay, does that make sense? So we have these three images. Now imagine that I just take these three images, or I take these two images, the tennis ball and the picture of St. Peter's Basilica, and I just fit them over each other. Let me bring my face back here. There we go. So you don't have to have the Jupyter Notebook out. There are no coding exercises for you all in this lecture. All of the code in here is obviously going to be given to you, and it's going to be what we're going to be using throughout the rest of the semester, so don't worry, you're going to get plenty of practice. I care more about a kind of high-level intuitive understanding to a lot of the stuff in this notebook than actually being able to type up the code, okay? So I just ran this cell here, and I wrote this file, tennisballols, that contains all of the code to this problem. And to start, let me just show you the original image. So it should take a second or two to run. Here we go. So as you can see, all that I did was take this ugly image of a tennis ball and put it on top of St. Peter's Basilica. You should pretty clearly be able to see that it's obvious that it doesn't fit. I mean, a giant tennis ball in St. Peter's Basilica is going to look ridiculous no matter what you do to the tennis ball, but the lighting of the tennis ball is very clearly wrong, right? It's very bright. There should be some shadows here. It should kind of have this yellowish orangish glow to it that kind of just helps it fit in with the background a little bit better. So what I'm going to do is just use linear regression to adjust the lighting of the tennis ball. I'm not going to go into how I did that, but all of the code is in tennisballols.py, which is going to be in the zip file that I sent out, or that I already sent out. So you can take a look at that if you're curious. So I'm going to run this next cell here. And then when prompted, instead of entering original, I'm instead going to enter OLS and click enter. And there we go. So, it's not perfect. It still looks pretty ridiculous, but the tennis ball clearly fits better in the space. It's a little bit brighter here. There are some shadows here. It's a little bit brighter here. And the general hue to the tennis ball just fits in the space better. So pretty cool. Okay, so now let's jump into linear regression. Okay, so last week, Yiming went over a introduction to simple linear regression, where you have just one explanatory variable x and it has this form y equals mx plus b, which hopefully you remember from middle school algebra. But today we're going to go over a little bit more of a adult formulation that is more useful for prediction problems. So last week, Yiming wrote this formula as y equals theta naught plus theta 1x. Note that you don't have to use thetas for your coefficients. They are oftentimes written using betas or w. It's kind of annoying, but depending on what class you're in and what department that class is in, you'll oftentimes see the coefficients in your linear model written as either thetas, betas, or w's. So Yiming used thetas. I'm going to be using betas for the rest of today. And remember that to find the theta naughts and theta 1 that best fit our data, we minimize a quantity called the sum of squared residuals, or residual sum of squares, RSS, which is equal to just the sum of your residuals squared, where your residual is just your y value minus your predicted value, which is this right-hand side of the equation. So you just subtract this right-hand side of this equation from the y. So you just subtract it over, and that's called your residual. So you square that residual value, and then you sum them all up, and that's your RSS. So that's the value that we want to minimize. The proof is in last week's lecture, so if you're a little rusty on how this theta naught estimate and theta 1 estimate are derived, take a look. I'm not going to go over it again because we're not going to be using this formulation for the rest of the semester. We're going to be using the kind of matrix vector formulation, which is a little bit cleaner and, in my opinion, a little bit easier to understand. Note that in this case here, this theta 1 hat is your slope estimate, and this theta naught hat is your intercept estimate. But if you have more than one explanatory variables, which we're going to get to today, you're going to have more than two thetas, and then theta 1 hat is more than, it's not just your slope anymore, because you have a lot of coefficients on variables, which is printed out right here. So imagine that instead of having just y equals beta naught plus beta 1x, imagine that we also tack on like a beta 2 x2 plus beta 3 x3 plus beta 4 x4, blah, 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 up to beta d xd, where d is the number of columns in your data set, and then n is the number of rows. So let me give a more concrete example of a problem that might be useful for this. So imagine that you're trying to predict the height of maybe a baby that's going to be born, okay? So the value that you're trying to predict is called your response, and that's going to be your yi here. So maybe, it's the height of the baby in centimeters or something like that. So that's going to be your response value here. And then these x's, so xi1 to xid, are going to be the features of your data set that you want to collect to help predict the height of the baby that's being born. So, take a second to think about what possible features you might want to collect. This isn't question 2 in the Google form. Just think about it for a second before I get into it. So, one value, one feature, one variable that you're most definitely going to want to use is the height of the mother, right? The height of the mother is, a really large part of how tall the baby is. Notice how that could have been our x here for the simple linear regression case. We could have just said, okay, let's try to predict the height of a baby based off of the mother. And if the mother was the only data that we wanted to use, then we could just do this simple linear regression case and we'd be all set. But intuitively, you should understand that there's more than just the height of the mother that affects the height of a baby being born. For instance, the height of the father. So imagine that we had an x2 here, again, I is the number of data points in our data set. So in this case, the number of babies, right? So the number of babies in our data set is n. So for each I, so for each baby, we have the height of that baby's mother. We could have the height of that baby's father. We could also have, what else? We could have the gender of the baby if we know that. We could have the race of the baby. That sometimes has an impact on height. We could have the height of siblings if the baby has any older siblings. We could have the height of grandparents, uncles, aunts. You can imagine how there are a multitude of features that you might want to consider when trying to predict the height of this baby being born. Okay? So that's kind of the justification for multiple linear regression, where we have multiple features that we want to use and we want to take advantage of their predictive power. So hopefully you remember what a linear combination is from lecture 5. If you don't, I recommend that you take a look at that quick, refresh yourself, and make sure that you understand why we can rewrite this line here as this here. Okay? So this is the formulation we're going to be using through the rest of the notebook, y equals x beta plus epsilon, where epsilon is our error variables, and I'll talk about that a little bit later. Yi, like I mentioned earlier, is just a vector of our responses. So this is the n heights in centimeters of each of the babies, okay? X here is our feature matrix or our data matrix or our design matrix. There are a number of different words for it. I like the words feature matrix or data. You can just call it your data matrix. Notice how I put a column of ones here. This isn't something that you'll have to do in practice because a lot of, sklearn, which we're going to be using for modeling for the rest of the semester mostly, will do this automatically for you. This is your intercept column. So just like, so here we have this beta 0. And notice how when we multiply x, this matrix x by this vector beta, what we do is we basically just take this vector, we turn it sideways, and we multiply beta 0 by the first column of x, we multiply beta 1 by the second column of x, and so on. Make sense? So that's why we need that column of ones there, so that beta 0, our intercept term, gets included. Okay, take a moment to make sure that that notation makes sense to you. Again, X is an n by d matrix, where n is the number of babies and d is the number of features. So, like I just said, epsilon is our error term that adds noise to our linear relationship. Here's a nice picture that I like to use to explain how OLS is used to find our optimal values of beta. So this is just the simple case where we have one x and one y. Imagine that these black points are just your data points here. And then we have this blue regression line that we draw through the middle of the data points. And we want to find some blue regression line that has a slope b1 and an intercept b0. So we want to find some blue line here that best fits the data. Now, to find the single line that best fits the data, we calculate the residuals. So the residuals are the actual y value minus the predicted y value by that blue line. So it's essentially just this vertical distance here, okay? So those are our residuals, also sometimes called error terms. Okay, so make sure that this image makes sense. So we calculate each of these distances, and then hopefully remember from before, the next thing that we do is we square these distances, and then we sum them all up. And that's our, and then that's our residual sum of squares, RSS. Okay, so hopefully this image makes sense. We need to take a little bit of sidetrack to make sure you all understand a little bit of notation before we jump into OLS again. So imagine that we have some vector A. It contains the values 3, -4, 5. The L1 norm, denoted by this double vertical line here with a subscript 1 at the end, is the sum of the absolute values of the vector of A. Okay, so just hopefully that makes sense. You just take the absolute value of 3, which is 3, the absolute value of 4, which is 4, the absolute value of 5, which is 5, and you sum them all up. Okay, so that's what the L1 norm of a vector is. The L2 norm, in this case we're going to be using the L2 norm squared, is pretty similar. The notation is similar. We have 2 double vertical bars here, and then the subscript 2, and then the superscript 2 as well, to denote that we're squaring the L2 norm. So if we have some vector A, notice how the L2 norm is equivalent to A transpose times A again itself. So these two notations are equivalent, but we're going to be using the L2 norm. That's kind of the standard notation. So similarly, all what we do for the L2 norm squared is we take each value of A, we square it. So 3 squared is 9, negative 4 squared is 16, 5 squared is 25. So we sum them all up, and then we add them together. And that is our L2 norm squared. Okay. Hopefully that makes sense. Let's go back to what we were doing before. So remember how I just said that the quantity that we want to minimize is our residual sum of squares. Okay? So remember how we wrote our residual sum of squares before? I'm going to propose a new way to write them as the L2 norm squared of x beta minus y. Hopefully that makes sense to you. Let me scroll back up to this formula here. So take a look at this formula here. To get our residuals, our epsilon, all what we have to do is subtract x beta from y. So we just move x beta over here to this side, okay? And that's called our residuals. So that's what we have appearing right here inside the brackets, or inside the vertical lines. And then we take the L2 norm squared of this quantity. Or, quick question, hopefully you can recognize this as a vector and not just a single scalar or a matrix, right? Because when we multiply some matrix by some vector, we're taking a linear combination, so we get a vector in return, and then we subtract another vector, so we get a vector in return. So this x beta here is our predicted values. We're taking a linear combination of our data using some coefficients beta, so that we're taking this linear combination of our data, and this becomes our predicted values. So this will sometimes be denoted as y hat, but we'll get to that later. So we subtract y from our predicted values. We take the L2 norm squared, which hopefully you can recognize as the sum of squares, right? Because that's all we're doing here. We're squaring the values inside of A, and then we're summing them, okay? So this is equivalently the residual sum of squares, okay? Now for this argmin here, argmin beta, what this notation means is you can think of argmin like a function that returns the value of beta that minimizes this expression, okay? Oh, I should stop clicking on my screen. So imagine that we have, this beta here is unknown, right? This X matrix is our feature matrix or our data matrix. This we know. This is values in our data that we can just, plug in. We know these values. And because this is a supervised learning problem, we know our response variable y. So we have this data as well, right? This beta is unknown. The coefficients, so the intercept, the slope, the rest of the coefficients on each of our features in our x here, those are the unknowns. Those are what we want to try to optimize for. So that's what this argmin is doing. We find the values of beta. Remember, beta is a vector. So we find the values of beta that minimize this expression. So it returns another vector this time of our new betas, so our beta estimates. So that's why there's the hat here. In particular, these are called the ordinary least squares solution to linear regression, the OLS solution to linear regression. I will be denoting it as beta hat OLS. That's a pretty common notation, especially in the statistics department. Okay, so I basically put it out there that we want to minimize this expression, right? That's something that I've said a couple times already. Let's go over how exactly we can minimize this expression. So I'm going to define a function. Let me call it L of beta, okay? You'll hear this function called a few different names. I'm going to use the name objective function, okay? So I'm going to be calling this an objective function. So it's a function that takes in our beta coefficients and then returns the residual sum of squares. Okay, makes sense? Note how I wrote both formulations here, both the summation form and the matrix form. These two are equivalent. Okay. So let's rewrite this expression here. Notice how, if you remember here, the L2 norm squared of A can be written as A transpose A, where A is a vector. So we can do the same thing for what's inside of the L2 norm squared here too. Okay? So we can take what's on the inside, transpose it, and then multiply it by itself again. Make sense? This should look pretty familiar to you, even if you aren't too familiar with matrix operations. But you should be able to see, okay, yeah, I can like FOIL this, remember? Like first, outside, inside, last. So don't pay attention to every step here, but all what I'm doing is foiling, okay? First, outside, inside, last. So I FOIL and I get this expression, okay? That's just another step in the process. It's not super important that you understand every step here. So this function here, remember this is still a function of beta. The x's we know and the y's we know, but we don't know the betas. So remember this is still a function of beta. It can be proven that this function is convex. Okay, so so just as a reminder as to what convex means, think U shape. Okay, so I think there's a more formal definition about how if you like draw, people in Math 1A can probably correct me, but if you draw some sort of line between any 2 points above the curve, it never crosses the curve again, or something like that. There's some sort of definition about convex like that. You can prove this to be convex by taking the Hessian of it and then showing that the Hessian is positive semi-definite. Don't worry if you don't know what that means, but Math 54 people, you should be able to do that. So now that we have this convex function, our objective function, L of beta, let's do like a throwback to like AP Calculus from high school. What can we do to minimize it? We know that any critical point is going to be our global minimum because it's convex. So what can we do? This is Q2 in the Google form. So take a couple minutes, type down what you think the answer is, and then I'll get back to you. Okay, so hopefully you were able to remember from your AP Calculus days that all what we have to do is take the derivative, set the derivative equal to 0, and then solve for the variable that we're interested about. In this case, beta. Okay, so don't worry about each of the steps here. If you haven't taken Math 54, I do not expect you to know how to do gradients, but they're essentially just derivatives, but for matrices, okay? If you've taken Math 54, take a minute to go over each of the lines here and make sure you understand how each gradient is calculated. It might help you on a 54 final or something like that. But all what we're doing is we're taking the derivative of our objective function with respect to beta. We set that derivative equal to 0, and then we solve for beta again, okay? So once we solve for beta again, we derive this beta hat OLS here, just like before. Remember, this is what we're trying to find. We're trying to find the beta that minimizes this expression, and we just did that, okay? XTX inverse XTY. Notice how this is a closed form solution, okay? So we know the matrix X and we know the vector Y, so we know this closed form solution here. We know we know all of the values on the right-hand side, so this is a closed form solution. This formula is very, very, very powerful, and you will see many, many times in tests, in interviews. It's almost guaranteed that at some point in your life as a data scientist, you will be asked to derive this formula, okay? The ordinary least squares solution to linear regression. That's what it's called. Cool. So you went over inverses a little bit last week with Harry and Yiming, or I think that was Harry's part. It turns out that this inverse right here is sometimes hard or even impossible to compute. We'll talk a little bit about the cases where it's impossible to compute later. But for the hard cases, inverses are very complex operations and they're not very computationally efficient. So even though linear regression has this closed form solution here, we'll oftentimes use optimization algorithms like a gradient descent to approximate this beta hat OLS instead, just because it's so much faster and it's still pretty accurate. So we're going to talk a little bit about gradient descent later today, but first I'm going to touch on the closed form solution a little bit more. Okay, makes sense, hopefully. If you have any questions, you can shoot me a message on Slack or even comment on the YouTube video. I'll be checking it pretty regularly, and hopefully we can get it answered. Cool. So let's take a look at a data set here. Let's give a little bit more concrete example of what I've been going over. So don't pay attention to any of the code in this cell right here. This is all just preparing the data set. Remember how I said before that for any learning problem, we're going to want to split our data set up into 3 different sets: a training set, a validation set, and a test set. So a common split is 60-20-20. So 60% of the entries in your data set go to your training set, 20% go to your validation set, and 20% go to your test set. Okay? So that's all what I'm doing here. I'm just splitting up the entire MPG data frame into 3 different parts. Let's just take a quick second to look at the MPG train dataset. This is another oftentimes ignored part of machine learning, is just looking at the data and understanding each of the columns and how they relate to one another. Too often, domain knowledge is lost and interpretability is lost in favor of performance and stuff like that, okay? So really, really make sure that you take time to understand the data that you're working with. So we have this data set where each entry is just a car. The index here is the car name or car model name, I guess. This column here is the miles per gallon, or the fuel efficiency of the car. This is the number of cylinders for the engine. This is the displacement, horsepower, weight, acceleration, model year, so the year the model was developed, and then origin. If you don't know what the meaning of a column is, you can probably Google it and figure it out. Origin is the country of origin that the car manufacturer is from. So I think 1 is the United States, 2 is Europe, and 3 is Japan, maybe. I don't remember exactly, but you can just Google it, and this data set is very commonly used for education purposes, so it's very well documented. Okay. Cool. So I split this up, and the data set we're going to be working with for now is, why does my mail keep doing that? And the data set we're going to be using for now is MPG train. Okay. So the prediction problem that we want to be able to solve is predict the miles per gallon for a car model given all of these other data. So given the cylinders, the displacement, the horsepower, the weight, the acceleration, the model year, and the origin. We want to be able to predict miles per gallon. Okay, kind of a cool prediction problem. Thinking about the fuel efficiency of cars. How well can we estimate how fuel efficient a car is given other information about the car? It's kind of a cool problem. Okay. So we have this data matrix MPG train. Don't worry too much about the code in this cell. I'm just kind of playing around with the matrix a little bit to get it into a form that's easier for me to give this demo for. When you're using sklearn for all of this, you won't have to be doing this step, but let me just run these cells to show you a little bit more about what it's doing. Okay, so here I'm just printing out the shape of xtrain and ytrain. So there are 234 rows and 8 columns in our x, okay? So this is n and this is d. So this is the number of entries. This is the number of features in our data frame. Remember, 1, 2, 3, 4, 5, 6, 7, and then our intercept column is 8. Okay. Likewise, y, which is just this column of MPG right here, has 234 entries. Okay. So that's all that's doing, and then here I print out what xtrain is. So we have this intercept column here, and then we have 8 columns of features. Okay, so hopefully you have memorized the closed form solution for linear regression already. If you haven't, I basically just write it out in NumPy here. So here is xt, so np.transpose on xtrain. This is how you multiply matrices. This is x again. So this right here is xtx, okay? And then I want to take the inverse of that. So to take the inverse, I can just use np.linealg.inv, which hopefully you remember from last week, but if not, here it is again. So now I'm just taking xtx inverse. Hopefully you remember the next step is to multiply by xt, so that's what I do right here. And then finally, you multiply by y again, okay? So all I'm doing here is using the data that we have, xtrain and ytrain, to calculate the beta hat OLS. Okay, makes sense? Don't worry about the next 2 lines. This is just putting it into a nicer shape for you guys to see when I print it out. So, you'll notice here that we have our different coefficients. Okay, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 different coefficients. Remember, 1 coefficient for each of the 7 features, and then 1 coefficient for our intercept term. It's no longer a coefficient, but then 1 value for our intercept term. Okay, so that's right here, this first one, intercept term, and then 1 coefficient or 1 weight for each of our 7 features. Awesome. So this kind of like example here where I actually code out the closed form solution is kind of a toy example that you should really never do in practice. You might have to do it for a homework assignment or something, but there are a lot easier and faster ways to do this using scikit-learn. Okay, so hopefully you remember scikit-learn from last week. If not, this is kind of more or less how it works. You call this function linear regression, capital L, capital R. In this case, I'm setting the fit intercept equal to true so that the coefficients that I just calculated above match the ones below. You can also fit a linear model without an intercept term. Oftentimes, if you're in a high enough dimensional space, it doesn't matter whether you have an intercept term or not. But if you're in a lower dimensional space, I always remember having an intercept term. Okay. This is actually the default, so I don't need to have it set equal to true here, but I just explicitly write it out for clarity's sake. Okay, so I initiate the linear model right here by just calling this function. Okay, and then I fit the linear model, so I store it. I store the linear regression object as this variable linear model. Here it is again, and one of its methods is .fit. So this object here, linear model, has a lot of different methods. You can look up the documentation yourself. We'll be introducing quite a few of them to you today. But the first method that you always have to use is .fit. Okay, so we fit x and y. We fit our x train and our y train. Notice how I'm not fitting the entire data set x and the entire response vector y. I'm just fitting the training set subset of it, right? Because that's all what we want to use to fit our linear model. Not the entire data set, just the training data set. Okay? That's really, really important. You don't use the entire data set when fitting a linear model. So the next thing that you do is you set this object to the object.fit itself. Actually, I don't think you need to do that. Yeah, I don't think you need to do that step, but I do it anyway. And then here I just print out. Don't worry about this line. I just print out the coefficients that we got from sklearn. Okay, so these are the beta hats that we got from using whatever optimization technique underneath the hood this linear model .fit uses. Okay, so whatever optimization technique this uses, we can't see it without looking into the source code, but this is the coefficients that they output. When we compare them to the coefficients that I calculated here above, beta hat OLS, we notice that they're the same. True. Okay, makes sense? Awesome. So it doesn't, under the hood, it actually turns out that for most problems, scikit-learn will not use the closed form solution, like I mentioned earlier, because it's a lot slower than some other optimization techniques, but it still yields the same result in the end. Cool. Okay, cool. So now that we've established how to fit or train a linear regression model, let's go into evaluating it based off of our predicted values. So determining the effectiveness of a regression model is actually a pretty nuanced problem, but two of the most common metrics that we'll use and that people use in general are called the mean squared error and the coefficient of determination. This is also called R squared. Okay, so the mean squared error, I have a formula here for it. All what we do is we take the actual values y. So in this case, we take the actual miles per gallon of each of the cars, and then we subtract from it our predicted miles per gallon y hat. So we subtract our predicted miles per gallon for that given car I. We square it. We sum over all the cars in our data set, and then we divide to take the average. Hence the mean squared error. Okay? So this is just one metric that we can use to gauge the effectiveness of a regression model. The coefficient of determination, on the other hand, is often interpreted as the proportion of variance in our response variable, so MPG, that is captured by our explanatory variables, so the other 7 variables in our MPG dataset. Okay? Cool. Notice how because these two vectors of coefficients here are the exact same, it doesn't matter which one I choose for the rest of the notebook. Okay? I think I used beta hat OLS, but it doesn't matter. So don't worry too much about the code in this cell. Here, I'm just doing the same thing to the validation set as what I did to the training set. I'm just putting it in a nicer form for matrix operations and stuff like that. Okay? So notice how our validation set, which is 20% of our data, is a lot smaller. It has only 79 rows. Notice how the columns are the same though, right? We don't drop any of the columns. We use the exact same columns. It's just that it's a subset. It has smaller rows than the smaller number of rows than the training set. Okay, so we use this validation set to make our predictions. Okay, we never want to predict on the training set. We always make our predictions using the validation set. Okay. Remember that our predictions are just x beta. So x times or at, so x val at beta hat OLS. So we're taking a linear combination of the columns of xval using weights found in beta hat OLS. Okay? So we end up with this vector. Notice how it's a NumPy array, so it's just a vector of our predicted values. Make sense? And notice how if I take the length of it, 79, it's the exact same as the length of yval. Okay? So for each value in yval, we have a prediction yval pred. Oop, that's the wrong one. There we go. For each value in yval, or for each value in our validation set, we make a prediction. So for instance, this car here, we predicted had 29.06, has 29.06 mpg. Okay? So obviously the next step is to just calculate our residuals. Okay? So to do that, we just subtract. The acronym that I like to use is RAP. So residuals equals actual minus predicted, RAP, RAP. So we take our actual yval here, we subtract our predicted, and that ends up being our residuals. So again, we have 79 residuals because these two are vectors of 79, so we get another vector of 79. And then to calculate the mean squared error, it's really easy. We just have to square this vector. Remember, NumPy and operations are vectorized, so we don't need to use a for loop or anything. We can just do **2 and then np.mean. Cool. So we end up with a single number. Remember, because we're squaring and summing, we sum each of the elements, each of the squared elements in that vector, so we get a single scalar value, no longer a vector. Okay? This is our mean squared error. This number by itself does not mean much. Some models are going to have extremely high mean squared errors, some are going to have extremely low mean squared errors. Where it becomes useful is when you are creating different iterations of models and you want to gauge whether a change that you made to a model resulted in an improvement or a worsening of your model performance, okay? So this number is really, really useful for comparing different models that you're making, but is not particularly useful by itself. Make sense? What's more useful by itself is a residual plot. So Yiming may have touched on this very briefly last week. If not, look at it again from lecture 5. I will talk about it here though. So all what we do is we create this scatter plot where on the x-axis we have our fitted values or predicted values. Okay, so if you remember our vector of predicted values here, we have like, I think the smallest value here is like 4.6 or whatever. So we have a value here down at 4.6, right? That's our x-axis. And then our y-axis is our residual for that fitted value. Okay, so the prediction that we made for 4.6, the prediction that we made of 4.6 turned out to be quite a bit lower than what the actual value was. Because remember, we take the residuals equal to the actual minus predicted. So because the actual minus predicted here was almost equal to 10, you know, let's say like 8 or something like that, that means that the actual value was like 8 higher than our predicted. Okay? So that's what the y-axis is, our residuals. And a good diagnostic for our residual plot is that for our model to be good or to be appropriate, this, bring my face back, this scatter plot here needs to be a formless blob or cloud. So it can't have any pattern to it, okay? Notice how we kind of have this like parabola shape here. For lower fitted values or higher fitted values, the residuals tend to be higher, and then for fitted values somewhere in the middle, the residuals tend to be lower. This is called heteroskedasticity. That word was introduced in last week's lecture. If you want to review how to spell it, go back to last week's lecture. If we have this formless cloud, which is what we want to achieve in modeling regression problems, that's called homoskedasticity. So, you know, homo means same, hetero means different. So essentially we're looking for homo or same spread of residuals over fitted values. Make sense? We don't have that here though. Okay. And finally, the r squared, right? So to calculate the r squared, there's a really, really nice, easy function in scikit-learn just called dot score. So we just use the same linear model object as before, but we call dot score on our x-val and y-val, and it returns our r squared for our OLS problem. And it is 0.77. So again, you can interpret that as the amount of variance that is captured in our response by our explanatory variables. Again, 0.77 is actually reasonably high for an r squared value. It's not too bad at all. But again, because we have this kind of U shape here in our residual plot, this is probably not a great model. We're going to talk about in the coming weeks how to kind of correct this pattern and how to, perform modeling techniques that can kind of lead to better results. But for now, we're going to take a little bit of a tangent and go into polynomial regression. Okay, so let's talk about polynomial regression. The basic idea is, let's say that we want to predict miles per gallon versus displacement. Okay, so let's try plotting this. And you'll notice how it kind of has this curved shape here. Something that a straight line probably isn't going to be able to capture super well, right? If you were to, say, draw the line of best fit through here, you would draw a straight line that looks something kind of like this, maybe. But in actuality, I would rather have a curve here. I would rather have some sort of parabolic shape to help model this relationship. Okay? So for polynomial regression, you can have different degrees, right? Just like polynomial expressions from math class. So if you have polynomial regression of degree 2, your feature matrix is going to have 3 columns. It's going to have x0, x1, and x2. So your original matrix is x1, x to the power of 0. So your feature matrix, or your feature vector, because remember we just have one feature here, displacement. So displacement to the power of 1 is just displacement. Displacement to the power of 0 is just a column of all 1s, and then we have displacement squared, okay? So we now have 3 columns, okay? Here, let's create our data matrix of just displacement. So here I have this matrix, but it just has 1 column, displacement. Don't worry about this function. Just know that it performs polynomial regression using scikit-learn, okay? Where the parameters here are the degree of our polynomial. So again, if it's degree 2, then this is going to return a polynomial regression with those 3 columns. Our x, which in this case is just a column for displacement, and then our y, which is still just a vector for MPG. Okay, so don't worry about the code in this cell. Let's skip ahead to degree 0 polynomial. Okay, so before I show you what the plot of a degree 0 polynomial regression is, think about it for a second after seeing this feature matrix here, because this is the feature matrix that we're using. Why don't we think a second about what the prediction line is going to be? Turns out it's just a flat constant line. Hopefully that makes sense to you. We're taking this linear combination, but our feature matrix is just a column of 1s. Okay? So hopefully that makes sense to you. Obviously, degree 0, not a particularly good prediction model at all. It's basically just saying, I don't care what displacement is, I'm always going to predict 24 or whatever for MPG. That's basically all it's saying. Not a particularly good prediction model. Pretty dumb. Let's do polynomial degree 1. What does this look like to you? Just the feature matrix here. We have this intercept column, and then we have another column. Hopefully this looks like a line, right? And it does. So remember how at the beginning I was like, if you were to draw a straight line through this data, what would you draw? You'd probably draw something more or less like this. This is the simple linear regression solution where we have our slope and our intercept, trying to predict MPG from just displacement. But we can go further. Let's try a degree 2 polynomial. That's pretty good, right? We now have our intercept, we have the original column displacement, and then we also have displacement squared in our feature matrix, right? So we're going to have 3 different coefficients. And, it looks pretty good, actually. We had this kind of curve that we identified originally, and we wanted to be able to fit some sort of parabola to it, and this is pretty good. What happens if we go further? What would happen if we add 3, 4, 5, 6, 7, 8, 9, 10 polynomials? Something funky starts to happen. So notice how we have a bunch of really big numbers that we start to get. The original displacement squared, displacement cubed, blah, 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 all the way up to displacement to the 10th power. And then we do OLS again on that. And this is the curve that we end up getting. So take a second to think about what happens when we increase the degree of our polynomial. Notice how the curve just starts to follow the data more and more closely. It starts to become more sensitive to outliers or little changes in the data, things like that. Okay, so it becomes a lot more sensitive. That's basically the answer to this question here. This next question here, though, is going to be Q3. Question 3 in our Google form. Is our model still linear? Is polynomial regression, even if it's degree 10, is degree 10 polynomial regression still linear? Write down your submission in the Google form. Take a second to do that and think about it for a second. Okay, so hopefully you've been following along in the Google form too. It turns out that polynomial regression is still linear. So you might be thinking to me, what? This is clearly some curvy line. But when we talk about linearity, we're talking about linearity in terms of the parameters. Okay? We want our coefficients of our model to be linear. We don't care about x. We don't care about the x's. So let me go back up to the math formulation here. Okay, so actually let me go up even further. Here we are. So when we talk about linearity, we talk about linearity in terms of these betas, okay? When we do polynomial regression, we're placing exponents on the x's. So there could be like a 2 here, a 3 here, a 10 here. It doesn't matter. We could put any exponent we want here on the x, but this beta 1 is still going to be linear with y. There's still going to be a linear relationship between y and beta 1, even if x has some crazy power on it. Okay? Where a model becomes nonlinear is if we add some sort of transformation that no longer makes a linear relationship between y and beta. So if, for instance, we had some sine or cosine, and we put that around beta 1x, I1, so if we put some sine around all of this, or a cosine, then that becomes a nonlinearity. So then we no longer have a linear model. But as long as there's a linear relationship between all of your betas and y, it doesn't matter what you do to the x's, it's a linear model. Very, very common test question. Okay. So we just finished talking about regression problems. Let me go back up to the top actually. So we just finished talking about regression problems where we have some quantitative response. The demo I gave, it was miles per gallon for a car. Okay? So unfortunately, so far for this entire hour plus a little bit, we've only talked about this leaf of the tree, okay? Now we're going to jump over to this leaf, classification, okay? And the one classification algorithm that I'm going to talk about today is called logistic regression. Okay, so let's go back down to logistic regression. There it is. And I know what you're thinking, because why is there the word regression in the name if it's used for classification problems? Yeah, I agree. It's kind of annoying, but remember, logistic regression is used for classification problems, okay? Even though regression is in the name. Okay. More particularly, simple logistic regression is often used for just binary classification problems. So predicting ones and zeros, two different classes. There is forms of logistic regression for multiple classes, but for the demo today, we're just going to do the two-class case, a binary classification problem. Okay? To start talking about logistic regression, like we started talking about linear regression, there's a little bit of notation and definitions that I need to introduce first. First is the sigmoid function. So this is just a simple function, maybe you've seen it before in a calculus class, that takes in some value, x or z or whatever is on the x-axis here, and then it passes it through this equation here, and it maps whatever value z to the space 0, 1. Okay? So think about that for a second. We have some x value, anywhere between negative infinity and infinity. No matter where we are on that scale, this function is always going to return a value between 0 and 1, where it returns 0.5 when z equals 0. So there's kind of like a balance or inflection point at z equals 0. Okay. Now we are a statistics club, so hopefully you thought immediately of probabilities when I mentioned in the space 0, 1. Probabilities fall in the space 0, 1, and that's the reason why we use this function, as a matter of fact, to create some sort of predicted probability from some other value z, which I'll mention very briefly. Before I talk about z, though, I'm going to talk about the decision boundary. So basically, again, when we're dealing with a binary classification problem, 0, 1, and we have our predicted probabilities, which are mapped through the sigmoid function, we need to establish some sort of probability threshold where if a value falls above that threshold, we classify that point as class 1, but if it falls below that threshold, we classify it as class 0. Make sense? So for today, and quite frequently, 0.5, 50%. Smack dab in the middle, that's the most common decision boundary threshold, and that's what we're going to be using today. Note that you can change it, though, and when you do change it, it turns into a sort of parameter of your model that you can kind of twist around a little bit to help improve performance. But for today, we're just going to be using 0.5. Okay, so now to actually make our predictions z, and then our predicted probabilities p. This is where the regression part comes in, right? This should look very, very familiar to you. This is the exact same equation as above for linear regression when I introduced it. We're just taking this linear combination of our data x with some coefficients beta, okay? But instead of calling this y, let's call this z, because it's really just like an intermediary step, okay? We then pass this linear combination into the sigmoid function, right? That's what I'm doing right here, to obtain our predicted probabilities p. Does that make sense? So before, our predicted values, y hat, for linear regression is just x beta. It's just this here, okay? These were our predicted values for linear regression. For logistic regression, we have to go one step further. We pass it through the sigmoid function, and our predicted probabilities become p, okay? Now, hopefully remember this line here from linear regression above. This was our cost function or objective function, okay? We took the L2 norm of x beta minus y, remember? And then hopefully you remember that we took the derivative or the gradient of this function with respect to beta. We set it equal to 0. We solved for beta, and then we got the closed form solution for beta hat OLS, which was equal to xtx inverse xty. Hopefully you remember that. If you don't, go back up, review it a little bit. So that's what we did for linear regression, okay? For logistic regression, we have to use a different cost function. We have to use a different objective function. The objective function that we use for logistic regression, is called the cross-entropy loss. This is also sometimes called the log loss. Okay, so I'm not actually going to have you derive, or I'm not actually going to derive the cross-entropy loss. If you've taken Stat 153 and are familiar with maximum likelihood estimation, then that is how the cross-entropy loss comes about, but I'm not going to get into that. Regardless, I do want to explain it a little bit though, because the formula itself can look, a little confusing, and you might be wondering why it works. The objective function that we use for linear regression is a lot more intuitive and easy to understand. This one looks a little bit more complicated. So the idea comes about from information theory, and the idea of entropy, or like the amount of disorder in a system. If you've taken chemistry, you've probably heard the term before. Let me give you an example. So pi here, remember, is the predicted probability from before, which we calculated here, and then yi is the actual 0, 1 label of the ith row of our data set, okay? And the reason we have this sum here that just sums over all the rows of the data set. I'll explain why the negative is there later. But let's say that we have some row of our data set that is of class 1, and then the predicted probability, if we have a good model, is going to be somewhere closer to 1. Let's say 0.9 or something like that. This second part of the summation, because yi is 1, is going to drop out, right? 1 minus 1 is 0, so the second half of the summation just drops out, so we only care about this half, right? So we have 1 times the natural log of 0.9. So if you don't remember, the natural log kind of has this flipped exponential almost, where at 0 it has a limit approaching negative infinity, and then as you approach 1 or at x equals 1, the natural log is at 0, right? So if you have a good model, this pi is going to be pretty close to 1, and then the natural log of 1 is 0, right? So the closer your pi is for class 1, the smaller this value is going to be, and ultimately the smaller value you're going to be summing over all data points, right? Because remember, for objective functions, the goal is to minimize them, right? We minimize this objective function similarly to how we minimized the objective function here for linear regression, okay? So this was the case if our true label is 1. Hopefully you can see already how if our true label is 0, then this first part of the summation drops out because you're just multiplying by 0. And then here we're multiplying by 1 because we have 1 minus 0. And then we have the natural log of 1 minus the predicted probability. So hopefully you can see how this is kind of the opposite, right? So if we have class 0 and the predicted probability is hopefully our model's good and it's hopefully close to 0, then you're going to be taking the natural log of 1 or close to 1, which again is close to 0. So you're adding very little to the summation that you're calculating, right? Conversely, if we have a bad model, right? So like let's say we're getting a prediction wrong, and let's say that this predicted probability here is really close to 1, even though the true label is 0, then we're still going to be using this second half of the summation here. This is going to be 1, and then 1 minus some number close to 1. Let's say it's essentially 0. we're essentially taking the natural log of 0, which, as you remember, is like negative infinity, right? So then this summation here is just going to blow up and explode, and we're going to have like a really large value here. That's part of the reason why this negative comes into play. What we want to do is we want to ultimately maximize our likelihood, which is the same as minimizing this expression here. Okay. Cool. So again, I just explained that the goal of creating objective functions and cost functions is to be able to then minimize them, right? So we minimized the objective function for linear regression by using the closed form solution, right? We were able to just take the derivative, set it equal to 0, and solve. Remember? That unfortunately cannot be done for this cross-entropy loss. Feel free to take the derivative if you want. You can do it again and again and however many times you want, but the cross-entropy loss does not have a closed form solution. So if you remember me mentioning earlier, scikit-learn oftentimes will use gradient descent for linear regression anyway. Scikit-learn has to use gradient descent or a variation of gradient descent to minimize the objective function for logistic regression, cross-entropy loss. Okay. So I'm going to now jump into a little demo of logistic regression using scikit-learn. I'm going to use the same data set as before, and don't pay too much attention to this code. It's very, very, very similar to what we did before for the linear regression demo in scikit-learn. There are just some things that I had to change. Don't worry about this. Basically, what I'm doing is encoding certain values as binary, right? So I take oil expensive here. Before this was like before this was a character like strings, and I'm just turning it into zeros and ones because that's what I am going to use for the logistic regression part. Okay, that's going to be our binary prediction that we want to make. Okay. So again, similar to linear regression, I split up my data set into a train, test, and validation set. Okay, so that's what I'm doing here. I have my y-val as just the oil expensive column, so that's just as zeros and ones, and then I drop that from my design matrix, from my feature matrix, such that my feature matrix only contains the other columns. Okay? Cool. So notice how this is in scikit-learn now. So notice how the logistic regression functions work pretty similarly to the linear regression functions, right? So you just instantiate this logistic regression object by just calling the logistic regression function, capital L, capital R. We store that object as a variable. We then fit, just like before, we fit that object to our training set. Remember, I'm going to hammer it home again. Only fit your model, whatever type of model it is, to your training data, okay? That's why it's important to split off a validation set and a test set. Also, in case you were wondering, there cannot be entries that are in both, right? So they have to be unique. You can't have an entry that's in both your training set and your validation set, for example. Make sure that the training set, validation set, and test set are all distinct entries, okay? If you have duplicate entries in your data, that becomes a different story. And we might talk about that in the data cleaning. We'll talk about that in the data cleaning section. That becomes a little different. So back to logistic regression. Y-val here is just the column oil expensive here, which is a column of zeros and ones. And this column here is, as you can see, just zeros and ones, okay? So that's our binary. Y-val pred is the result of using the .predict method for our logistic regression object, our scikit-learn object, LR. So when you do lr.predict xval, what scikit-learn is doing is predicting zeros and ones for each of the entries in xval. Okay? Remember, predict on your validation set, train on your train set. Fit on your train set, predict on your validation set. So as you can see, these two vectors or arrays are the same length, which is good. They're all zeros and ones. They look a little bit different though. So a natural question is, how do we evaluate these, right? Like how do we measure the difference between these two? How much different are they? And I want you to think about it for a second. I actually have it written down right there. Let me scroll up a little bit, and I want you to think about it for a second. So you have these two arrays of zeros and ones. How would you measure the similarity or accuracy, hint, hint, between these two arrays? So yeah, accuracy is a good place to start. Basically just compare each of the values element-wise in each of these two arrays and see how many of them you got right. See what proportion of them you got right, right? So if this is an array of length 79. So let's say that we got, let's say that 76 of the 79 are matching, then our accuracy would just be 76 divided by 79, okay? So yeah, accuracy is a great place to start, but to kind of show you one of the drawbacks of using just accuracy, let me propose a hypothetical situation. Imagine that you have a data set where the true values, the true binary values of your data are all ones, okay? Or it doesn't have to be all ones, but imagine that they're almost all ones. So maybe 99% of the values in your data are ones, and then there may be some zeros, okay? You could create a predictor, a very dumb predictor, that just predicts 1 every single time, okay? And you would have over 99% accuracy, right? Because there would be only ones that you would be trying to predict, right? So that's kind of one drawback of accuracy, right? Because you're going to miss all of those edge cases where, oh yeah, this scenario happens to be 0, okay? So to really get a better idea of the balance between zeros and ones between your different classes and your accuracy for each of those two different classes, you need to set up what's called a confusion matrix. So I mentioned in the beginning of this lecture, if you skipped over the beginning, go back to the beginning. I mentioned in the beginning of this lecture that I've been asked dozens of interview questions that have answers in this notebook. And this right here, a confusion matrix, I've been asked 5 times by 5 different companies. They love to ask you how you evaluate a binary classifier. And so many people just say, oh, you can do accuracy, and then they're done. But if you just say accuracy, you're wrong. You have to set up a confusion matrix. There are actually other things in addition to a confusion matrix that you should do that I'm going to talk about next, but a confusion matrix is the bare minimum. So basically all what you do is you set up your positives, negatives, or ones and zeros for both the actual values and then the predicted values, right? It's pretty simple. So if you predict 1 when it's actually 1, that's called a true positive. If you predict 0 when it's actually 1, that's called a false negative, which is also your type 2 error, or it's called the type 2 error. If you predict positive, but the actual class is negative, then that's called a false positive, which is a type 1 error. And then if you predict 0 and then the actual class is 0, then that's a true negative, right? So hopefully you can see how accuracy, which is in the bottom right corner here, is just defined as the sum of these two, true positive plus true negative, divided by the total number, n, right? These other four terms, these names are sometimes hard to keep straight. I oftentimes have to like keep on Googling them to remember them. These names are sometimes hard to keep straight. For our cases, we're going to focus on just precision and sensitivity, which is also called recall. Okay? So there's a really nice function in scikit-learn again that helps set up a confusion matrix for you. It's called confusion matrix. You could also compute it by hand if you preferred. But again, scikit-learn has functions for most of what you would want to do. Okay. So now what I'm doing is for the, I think it was 79, for the 79 entries in my validation set, I'm going through each of these zeros and ones, and I'm classifying them as either a true positive, false negative, or classifying each of our predictions as either a true positive, false positive, or true negative. Okay? And then I'm calculating our accuracy like this, just like in the diagram here, okay? So we see that we get like an 81% accuracy, which again is very, very case specific and problem specific. For some problems, for some binary classification problems, 81% is fantastic. For some, it's horrible, right? So it very much depends on the context of the problem. For our purposes, it's really only useful for gauging when you're comparing multiple models. For any one model, if you're making different iterations to the model, similar to R squared or similar to the mean squared error from regression problems, a lot of these metrics are only useful when you compare it to different iterations of the same model or similar models on similar data. And here's our precision and recall. So they're a little bit lower, but they're still high enough that I'm not too concerned, right? If you see your precision is like much, much higher than your recall or vice versa, then that's a little bit concerning. That means that your model probably is not doing as well for one of your classes as the others. Like, so for instance, maybe your model is really good at finding and correctly identifying class 0, but not class 1, or the opposite, okay? There's also a lot of research done around, confusion matrices are, I mean, when you write it out and we think about it, it kind of makes sense. But if you open up, actually, I'm going to open it up right here. There's a lot more, as you can see here, there is a lot more to a confusion matrix than I told you now. But again, for our purposes, accuracy, precision, and recall is about all that we're going to focus on. Okay, so confusion matrix is a must. Every single binary classification problem, evaluate it, always set up a confusion matrix. The other tool is called an ROC curve. So it stands for receiver operating characteristics. I don't really know what those words mean, to be honest. I just know them as ROC curves. And this is what they look like. One metric that we can calculate from them is called the AUC, which is just the area under the curve. So let me explain what's going on here a little bit, and then I'll go back up and show you the code for it. So on the x-axis here, we have our false positive rate, okay? And then on our y-axis here, we have our true positive rate. So remember, these are similarly calculated just from the confusion matrix. And what we do to calculate this curve here is we vary our decision boundary threshold from before for all possible, or for all values between 0 and 1, such that the change in the boundary causes one of your data points to switch, if that makes sense. If that part didn't make sense, just think of this as varying your decision boundary threshold from 1 to 0. So it's important to remember it's kind of backwards, but the lower left corner here has a decision boundary, has a model with a decision boundary of 1, and then the upper right corner here has a model with a decision boundary of 0. Okay, you can't really see it in this plot. Sorry about that. But the blue line here continues right here along the vertical axis, and then along here for the horizontal axis. And so the blue line will always go from this point in the bottom left corner to this point in the top right corner. Okay, so this point in the bottom left corner here, like I just said, we have a decision boundary of 1. Okay, so when we have a decision boundary of 1, we are always going to classify a point as 0 or as a negative, as a false, right? So likewise, when you only classify points as negative, your true positive rate is going to be 0 because you're not classifying any positives, but then your false positive rate is also going to be 0 because you're not classifying any positives. Antithetical to that, when you have a decision boundary of 0 up here, you're only going to be classifying ones. You're only going to be classifying, or I shouldn't say you're only going to be classifying ones. You're only going to be classifying points as 1. You're only going to be classifying data as positive, regardless of if it's actually positive or not, right? So because of that, your true positive rate is going to be 1 because you're going to get every single positive correct. But then your false positive rate is also going to be 1 because you're going to incorrectly guess every single 0 as 1. Make sense? So as you can see how there's kind of like a piecewise function here, or piecewise line here, that wiggles a little bit as we decrease our threshold. So we decrease our threshold left to right. And one kind of useful metric that we can calculate from this blue curve right here is the area. So we can calculate the area under it. Okay. So this model here has a AUC of 0.9. The AUC can be interpreted as a measure of the ability of our model to separate between two classes. So I wrote it down here, and an AUC near 1 means that our model has a very good ability to distinguish between two classes. Then an AUC of 0.5 means that our model is just randomly guessing. Okay, so you can imagine that a blue line with an area of 1 would just go straight up like this and then straight over like this, right? So that's kind of the perfect model, okay? Straight up and then straight over. So eventually you're going to get some sort of curve that ideally gets close to that, but it's pretty much never going to look exactly like that unless there's something wrong with your modeling techniques. And then similarly, where would actually, so this is going to be question number 4, Q4 in your Google form, in the Google form that I sent out with this to measure your questions. The question is, you can just explain it in terms of the graph here. Where would the blue line lie if we had a dumb model that was randomly guessing with 50% probability each of the two classes? So take a second to look at the plot, think about it. Imagine where you would draw the blue line if we had a completely random model. Okay, so remember how I just said here that we have an AUC of 0.5 if it's completely random? So this occurs here along this dotted red line, okay? That's why the dotted red line is there. It's kind of to give you a base mark or a bench line of what a completely random model would look like, right? Conversely, think for a second, you don't have to write this in the Google form, but think for a second about what it would mean if your blue line looked like this. If you had an AUC of 0, if it went straight along this horizontal axis and then up. Or even if it was somewhat curved like this, but maybe it was flipped over this line. So maybe you had some sort of curve in the bottom half. What would that mean? Take a second to think about it, but you don't have to write it in the form. So if that happens, if that occurs, you've probably made a mistake somewhere. You've probably mixed up your classes somewhere throughout the data wrangling or modeling process. But essentially what it means is your model is doing the opposite of what it should be doing, right? So it's taking its zeros and calling them ones, and it's taking its ones and calling them zeros, okay? To fix that, you should probably try to find an error, but you can always just flip the sign or flip the ones and zeros for your classes, and then you would have a AUC of some value above 0.5 again. Your blue line would be in the top left corner, so it'd be fine again. So, but that should never happen. So if that happens, you probably have an error. Okay, so this is the last part of today's lecture. I hope you enjoyed it. If you, again, want to take a little break, feel free to pause and do so. There is still one question remaining in the Google form, so make sure you stay tuned for that. Okay, so I've talked about gradient descent quite a bit so far today, but I haven't actually told you what it is yet. I like to give a more intuitive understanding and kind of like an analogy for it. So imagine that we have this valley here, and it's covered in fog. Okay, so theoretically there's a bottom to the valley somewhere, but you don't really know what it is. And imagine that I pick you up and I randomly put you down somewhere in this valley. It might be near the bottom, it might be near the top, it might be really far away, it could be anywhere, okay? But I place you down in this valley somewhere in the fog. And the fog is really dense, okay? And you can only see one step in every direction, okay? So if you turn around in a circle, you can only see one step in every direction. That's how dense the fog is. So kind of like naturally, you're like, okay, I want to get to the bottom. I'm filming this on St. Patrick's Day. Let's say there's a pot of gold at the bottom and you want to get there. So you want to take one step in the steepest direction downwards. Does that make sense? I mean, that's what I would do if I wanted to get to the bottom. I would find whatever the steepest direction is and then take my one step in that direction. Okay? Then my view space, the area around me that I can see, would change. Right? Because I'm in a new location, so I can see a different area of the valley now. It's still only one step. I can still only see one step around me, but I can kind of recalculate where I am, recalculate the steepest direction downwards, and then take another step, and so on. I can continue doing that until I get to what I think is the bottom. Okay? That's pretty much what gradient descent does. Here is a nice little picture of it. So this black dot here is maybe an initial starting position. What we do is we calculate the gradient or derivative at that location. We find the steepest direction. Because this is just a parabola here, when we calculate the derivative, the steepest direction is easy to find. You can imagine how if you have higher than two-dimensional space, though, you can imagine how it becomes a little bit harder to calculate. But for this example here, I'm just going to deal with parabolas and 2D. So you calculate the derivative, you take a step in that direction, and then you repeat. So you keep doing it again and again and again and again and again until you get to the bottom. I'll go over how you know you're at the bottom in a little bit, and it's actually a pretty tricky question to be able to definitively say, I think I'm at the bottom. But to do that first, let's just take a look at a very explicit example. So imagine that we have some polynomial function, f of x. So throwback to calculus days, let's let f of x equal to x to the fourth minus 3x cubed plus 2. Okay? So we then need to know, I type it up here in Python, and then we then need to know the derivative of the function. Okay? So we take the derivative of this, and we get 2x minus 9. Okay, so the next step is, oh, here I just plot out the function. Okay, yeah, so this is the function we want to minimize, right? Here I'm just plotting f of x. Now this is the code for the gradient descent algorithm, okay? It's not particularly long. I'm not going to go over every step of the process for the sake of time, but you can go through this on your own, and I'll explain what some of these hyperparameters mean, but you can go through this on your own if you're interested. I care more about a high-level understanding of gradient descent is an optimization algorithm, a fast optimization algorithm that we'll often use to minimize our objective function. That's what I care about more. So here is a visualization of, let's actually run it again. That's not a very good visualization. So let me run these cells again. This one's a little more interesting. So this green point here is our random start point. So this is where I randomly placed you on the valley. This orange was the minimum we found at convergence, okay? So to reach convergence, one of the parameters you have to choose is the precision, okay? So here, 0.0001 is kind of like a standard precision for convergence for gradient descent, but it can be changed. Regardless, here I have a little print output of what our random start point was. So it was -20. So it was really far away from the minimum that we ended up at. And we took 422 steps, and the global minimum eventually occurred at 4.495. So if you remember before, the derivative was this: set the derivative equal to 0, solve. The minimum should have been 4.5. So 4.5 is what we were trying to achieve. We achieved 4.495 in about 422 steps when we were pretty far away. Okay, pretty cool, right? I can run this multiple times, and no matter where this green dot is, because we have a perfectly convex function, I'm always going to get an orange dot right around 4.5. Pretty cool. So the last question that I have for you is to think about drawbacks of gradient descent, okay? So one of the parameters that we have to set is your step size. This is oftentimes called gamma, okay? Step size I used here is 0.1, so that's pretty small, right? That's a pretty small step size, but again, you're multiplying it by the gradient in that direction. So 0.01 or yeah, 0.01 is a pretty reasonable and common step size. So what would happen potentially if our step size was really big? So imagine we had a step size of like 20 or 30 in this case. What do you think could happen to this gradient descent algorithm here? So take a second to think about it. Okay, so one thing that can happen is it never converges. You go on infinitely. So imagine that we randomly start here. We calculate our gradient and we know we want to go in this direction, but we take such a big step that we jump all the way up here. Let's say we do it again. We take another big step and we go all the way up here. I don't think you can see my cursor anymore, but you can get the idea. It's possible if your step size is too big to kind of bounce back and forth, going up between two sides of a curve, okay? So that's something that can happen. Even if you have a strictly convex function, gradient descent can sometimes fail you. Okay. That being said, there are a lot of variations to gradient descent that can help handle some of these cases, or cases where you don't have a perfectly convex function, right? So maybe you have some sort of polynomial function that has multiple minimum and it doesn't have, and you're not sure if the minimum that you found is actually the global minimum or if it's actually just a local minimum. So that's actually a really big problem that a lot of people spend time researching in machine learning, is how do you know that you're actually at the global minimum and you're not just stuck in some local minimum? Okay, so there are a lot of variations to gradient descent. A lot of them, there's one called stochastic gradient descent, which involves kind of multiple gradient descent iterations with random starts, and so on. I'm not going to go into them today. Again, I think that's a little bit beyond what we're going to be doing this semester, but gradient descent is really important. Okay, so again, hopefully you have answered all 5 of the questions that I asked in the Google form. I'm not going to say them again for those people who just watched the end. I'm going to make you go back through the video and find them when I say them. Hopefully you enjoyed this video. I think that this format works a little bit better than last video. I know that the last week we wanted to use a whiteboard for some of the linear algebra material, but a whiteboard was less necessary. It would have been nice today, but it's a little bit less necessary. So I think that just screencasting or screen recording my Jupyter notebook is a little bit more effective. Also, I'm going to add, I've added questions at the end of the Google form for feedback and stuff like that. So please do fill out those questions too. Otherwise, a couple more reminders and announcements. Part 3, the third and final part of the intermediate project, is due Sunday. Please get in touch with your partners. Everybody's having to social distance themselves, but you can still collaborate on your notebooks. If you're having trouble and you're not sure the best ways to share code with each other, reach out to me and I can give you some suggestions. Other than that, the week after this is technically spring break for us, so we're not going to be releasing a new lecture until the week after that. So it's going to be quite a while before our next meeting or our next lecture, our next video that we put out. But just to give you a little primer, it's going to be actually, let me see what we have scheduled next. Also, if you haven't found it already, we do have a GitHub that's public. So we post all of the lecture folders here in case you lose any of them or anything like that. So lecture 6 is what we just finished. Next up is going to be the bias variance trade-off and regularization. So a little bit of motivation for that. Remember from back up here, I kind of warned about overfitting, kind of having a red line that tries to memorize or follow too closely to your data. This is called overfitting. That's going to be a lot of what we talk about in the next lecture. So again, thank you for watching. Please fill out all the questions in the Google Forms. And other than that, I will see you soon.